Hello all. So this is a project that I was working on to make a presentation of my project and share in the YouTube community, and together we can learn. So the project I was working basically, yeah. So this is for antenna measurement. We usually have uh, like spectral network analyzer, antenna or coupler, or maybe a band pass filter, or maybe an attenuator. We uh, we we are interested to calculate its scattering parameters to know how much there's reflections in its port. So we all know that inside we have nano VNA, which is uh, I mean still expensive depending on its bandwidth. And in the right hand side we have very expensive VNA. These are quite expensive. They have very there is called FPGA inside it, and a very high quality PCB. So yeah, so they are quite expensive, and there are some open source projects on this thing. In the GitHub you can find how open like VNAR design and all. If you are interested, I will be in my description. If you are interested, you can see them. Okay, so this is this is how we calculate this is scattering parameters. So I was thinking to, I mean, it is not something new. This is a concept. So I'm a PCB designer, and I'm interested in designing this antenna using, I mean, CST, or we also have OpenEMS tool. I was thinking to make a very handy and inexpensive hardware, test my antenna to to see if to see its reflection and all. So this is what I was thinking. So I mean, here in this portion I will be using two AD8314 IC, which is from analog device. And this is, I was surprised to learn it is quite inexpensive, very inexpensive. So the idea is, and because I do not have any signal generator, so I was thinking to use like something like this. So I have um, this Seed Xiao microcontroller, and over here I have this UFL antenna port. Okay, so from here I can get 2.45 gigahertz because I do not have this, and usually I deal with 2.45 gigahertz ISM band, and I was going to feed that. Okay, I understand there is a 50 ohm characteristic impedance and all, so I will definitely consider that. Okay, so there is something like coplanar web guide on something. So in another video I will be explaining that as well. Even I have I have designed a digital attenuator. This is the first, I mean, of this project. Over here, if I can increase, um, I wanted to show you. Okay, I cannot create a zoom here, unfortunately. So over here, this is This IC, this is an ESP32 IC, bare chip over here, and this is the PCB antenna, and this is again two layer PCB. And okay, I will be explaining this thing like 50 ohm and the concept which CPWG or something. I mean how 50 ohm transmission lines, I mean why it matters, why we should care about the trace width and the gap, and why should we place via. So I will be explaining that in upcoming videos. Okay, um, over here. So this is the idea. Now I will be feeding the 2.45 gigahertz to this coupler from this Xiao MG24 Sense or any microcontroller that deals with 2.45 gigahertz basically. And the important thing to consider is to check whether I mean what power that UFL antenna or UFL port is providing. Because why it matters? It is because such ICs like AD8314, you can see it has it can deal with minus 45 dBm to 0 dBm. And what is the power we are injecting? It is 13 dBm. So definitely it will it will fry, or it will destroy the this IC. So we need something like an attenuator to lower this power. And why we need this coupler? Okay, now let me explain some. Let me give a brief idea about a directional coupler. This is a directional coupler. In the right hand side you can see. So again, depending on the frequency, um, uh, they can have different shapes, sizes as well. And since we are dealing with 2.45 resonating frequency, so we can design using FR4 material. um, Not a big deal. But if we go with the higher frequencies, if we increase our frequencies, then it's a better idea to design using a waveguide, because there will be loss in the material. So that is why what loss you might ask. So there is two different kinds of losses which is usually introduced, and those are um, those are dielectric loss, okay, and the conductor loss. Conductor loss is not uh, very much affect this directional coupler, but it is the dielectric loss. FR4 material, for example, it is very lossy material, so we need some other dielectric material like there is something called Rogers and so on. Okay, the idea, what is this, you might ask. So usually uh, if let me explain you. If suppose this is two transmission lines, okay, they are placed very near to each other. So if RF signal is introduced to the above uh, uh, this above transmission line, an electromagnetic effect will be introduced in the second line. Okay, that is the principle of working a directional coupler. Now if there is again, this thing depends on the distance between or the gap between these two transmission lines. If they are more closely packed, then there will be more power in the second line. So this is the principle basic. So this is the idea behind this device. And now imagine if we put something here, okay, or short circuit or open circuit, how this will affect. Now if there is a if we suppose if we put something like which is not suppose we put a load here which is not 50 ohm. So in that case there will be some reflection. Okay, so that reflection we can measure that reflection from port here. So this is the idea. And in the right hand side you can see this is port 1, this is port 3. So if we are injecting RF, so uh, some electromagnetic or some RF signal will be introduced in the port 3, that is called coupling, or that is called coupled uh, port. So depending on, for example, if we look to this directional coupler here, it it says it has 40 dB. So that means the power which we are injecting here, we will get 40 dB, I mean minus 40 dB here. Okay, and we all know there is a formula how dB and watt is related. I mean we all know that power in decibel scale is dB is equals to 20 times log of um, if 20 then it should be voltage, I mean 10 log of power, that is the thing. So if we are giving power 1 here, we'll get minus 40 dB here. So based on that we can calculate. Okay, I do not remember exactly, so that is why I'm not telling how much power we'll get, but some factor will be definitely reduced here. Okay, so this is the idea here. Already discussed why we need attenuators. And yeah, because I don't have a signal generator, so I'll be using this kind of a microcontroller. And this is my, although this digital attenuator is not required because we can use something like this, but still I am designing this thing. And now why I am, I mean, do I really need an ESP32 to control this digital attenuator? The answer is no, definitely we can. I remember, okay, I can create a zoom here. Okay, you can see there are 4 different pins coming out from this. Okay, this one. So there is some logic, like truth table is, if we Google about this microcontroller, you will definitely found how this I mean this digital attenuator is working. There is some truth table. So we have 6 different voltage levels, V1, from V1 to V6. And if I suppose if I keep all those signals low, then I will get some different uh, attenuation factor. And if I, so there are some you got the point. If I um, put V1 high and other low, then I'll get definitely different attenuation factor. So that's the idea. Okay, over here, okay, this is maximum I can create zoom, no more zoom I can create. Yeah. Okay. Okay. I cannot create a zoom and use um marker. Okay. No problem. Okay. So how this is working? If we ignore this transmission power injecting to our to our ICs, to our RF IC, which is very low power consuming device for the moment. Let's assume we are adding some attenuators in the incoming ports. Okay, so we can all we need is some power in this range to our ADC IC, AD8314 or RF detector IC, and it will develop a voltage. So what we are doing, we are calculating forward power and reflected power of which of this device, of this antenna. This is our device under test, which is connected to the to the isolated port of this coupler. So in if our antenna is not, I mean, if it is not, not absorbing all the powers from our transmitter, then there will be some reflection, and that is what we are studying the reflected power or the reflected voltage standing wave. And we are this IC, we are using here two ICs, two IC AD8314 IC here, and it will develop some voltage depending on the RF amplitude. Yeah, and we are going to read that voltage using any microcontroller of our choice. For example, like an Arduino Uno. So we can we can read its voltage in its analog pin, through its analog pin, and we can see them and we can project them in the display. Uh, so this is the idea, and this is how this is basic this is a basic mm, peak detector circuit. So we can imagine an AC signal. We can imagine like that. Suppose this is the AC signal, okay, which is coming, and let's assume this is an ideal diode here. So this is forward biased, okay. So as a result, only um, I mean only top or the positive portion of this signal will be allowed here. As a result, this voltage or the positive half will be stored here, and we will get some voltage at this node. Okay, maybe depending upon, suppose this is 0 and suppose this is 5 volt. We are considering this is an ideal diode, so there will be no barrier voltage, and we'll get some voltage here, definitely less than 5 volt. This is what this is the idea here. But let me tell you, when we are going to, higher frequencies, so inside this IC, this IC, inside this IC we have, there is something like PLL, phased locked loop or something, and there is voltage control oscillator. So it is not that simple. Why? Because this is, you can see this IC is working for the frequency. I do not remember exactly, but in the range, around in the range of 0.8 or 5 to 2.7 gigahertz. So this is, we can imagine another video on this topic. Okay then, bye. Thanks for watching.